Hello and welcome to my talk. My name is Mykola. I'm a PhD student at Vinnytsia National Technical University. Today I'm going to talk about a new metric of categorical distributions for topic modeling problems with Akin categories. Let's start with the problem statement to give you a little bit of intuition of what is this all about. Consider the problem of searching researchers to work on a common project, where we want to find researchers that work in the same area. For this example, we assume that researchers are represented as a distribution over some research fields, which is shown here in the form of vectors. So each coordinate of the vectors here represents a research field, and from here on and through the rest of this talk, I'm going to refer to coordinates of the vectors as categories to make things more clear. And the distribution is categorical because each coordinate represents a category from some domain field. The problem of finding collaborators to work on a common project usually consists of finding the most similar researchers by some given criteria. That means that we have to find the similarity between two vectors. There are many available metrics in the literature, but for this example we are going to use Chekhanovsky metric, just to show you why we decided to come up with a new metric. So since values of the vectors are normalized in the range from 0 to 1, Chekhanovsky metric gets simplified to the intersections of two vectors, which is a minimum. Since most of the values in vectors are 0, the similarity between each researcher equals 0.4. And that's the problem because these given researchers, all of them have the common research field. But for example, researcher B should be more similar to researcher A because researcher A has the information system and technologies, and researcher B has system analysis that are more similar than to marketing. So researcher A and B should be more similar, but they are not. And that's the topic of this talk. I'm going to show you what we did to improve the Chekhanovsky metric to take into account the kinship, or we may as well call it relatedness, of categories that are these vectors' coordinates. Let's move on to the literature review. As I said, there is a lot of research on different distance similarity metrics. Here you can see some of the most popular metrics, and I encourage you to explore more in this paper if you are interested. The key point here is that we didn't find any metric that would take into account the kinship of categories, so just using an existing metric was out of question. Let's set up the formal problem statement. Given two objects x and y, similarity of which is to be found, each object is represented as a distribution over some set of categories, which is essentially just a vector of values. The vector takes values in the range from 0 to 1 and is normalized. Given that, we propose to find the similarity between two objects x and y as a sum of two components. The first component is Chekhanovsky metric, which is basically just the intersections of two vectors. The second component is slightly harder to understand, but it is just a sum of what we call a kinship coefficient and a category residual, which I'm going to explain in a moment. Now let's see an example of finding the similarity between these two objects represented on this plot. On the x-axis we can see the categories, and on the y-axis the membership's degrees of objects to categories. Here the first component of the metric is just this hatched area, which is basically the intersection, and it equals to 0.4 plus 0.1 3 times, which is basically 0.7. The second component is slightly difficult to find. First, we find the residuals using the following formulas. The residuals are these values that are left after the intersections. So here are the residuals. We find them from the point of view of x and y separately. So for example, from the point of view of x, the residuals are going to be 0 because here there is nothing left after the intersection, 0.2, here is 0.1, and here is 0. From the point of view of y, the residuals are going to be 0.3, 0, 0, and 0. Then the residuals are composed into a matrix to simplify further calculations. And this is a kinship coefficient, which is basically a matrix of values, a binary relationship between categories. The kinship coefficient, for example, for two categories A and B is just a number from 0 to 1, which is basically the level of relatedness or kinship between two categories A and B. So for example, for this plot, for these two objects, if the kinship matrix is defined as follows, we get the second component of this matrix to be equal to 0.1, which is basically a 14% increase in the original value of the matrix. So based on that, we conducted 18 series of experiments. In each series, 5,000 pairs of objects A, X, and Y are generated. The numbers of categories M from 2 to 70 with a step of 4. And the data is sampled from the generalized Pareto distribution. It can be seen from the figure that the similarity values are in the range from 0 to 1. As the number of categories increases, the spread of results decreases, and the median of distributions does not depend on the number of categories. Let's see the distribution of kinship contribution, which is basically the second term of the metric. The median of this value increases with an increase in the number of categories. The increase in the median probably indicates that as the number of categories increases, a large number of weak ties between Akin categories make a significant contribution to the following term. This contribution of many pairs of Akin categories is tiny. It looks as a noise, but the sum of huge number of noise contributions turns out to be large. The need for a new metric is primarily due to the need to identify specific cases with strong crossover effects due to Akin categories. Also, the decrease in the number of outliers indicates that noise kinships make it difficult to detect such pairs of objects. Because of that, we propose to filter out the noise contribution of Akin categories. We assume the kinship to be noisy if the kinship coefficient is less than 0.05. Box plot diagram of the noise kinship distribution is shown here. It shows that the median noise contribution increases linearly, and the maximum value is at the level of 0.12. After noise component elimination, the box plot diagrams of the Akin categories have the following view. After the noise elimination, we can see there are much more outliers that indicate that the metric is able to identify cases of strong interaction across Akin categories. And the median value is almost doesn't change as the number of categories increases. And here you can see the diagram with the noise elimination, which is basically the same as without. Let's conclude the talk. We proposed a new metric that improves Chekhanovsky metric by adding the kinship component. The metric was further improved by eliminating the noisy kinships, and the metric can be used for topic modeling tasks in which, when evaluating the similarity of two objects, it is necessary to take into account their membership to Akin categories. Such tasks can be the selection of reviewers of research papers and theses, the analysis of the similarity of text, documents, and many other tasks. That's all from my side. Thank you for your attention. If you have any questions, do contact us and we'll answer them.